OChem 1, how in the heck are ya? I'm so excited. I'm not gonna lie, I'm drinking a latte right now, so I might be just a little bit hyper. Plus, this is one of my favorite topics. We're gonna tackle some pericyclic reactions. I love pericyclic reactions. Let's define pericyclic. That means within a cycle or within the cycle. And what that's gonna mean when we draw our mechanisms, we're going to draw a polar mechanism, but we typically have a nice flow of our arrows. We kind of flow with those electrons. We're going to flow in this case as well, but we're going to flow in a ring. That is what our pericyclic means. We're going to start and end in a ring. So in fact, the order doesn't matter. You could draw this one first and this one second, or this one first and this one second. It doesn't matter. They're all going in a ring. So it's kind of exciting. If you watch the organometallics video, we're going to use one of our organometallics. It's one of our first reactions we're going to look at for pericyclic. We're just going to look at two. So we looked at our carbene in our organometallics section. So what's awesome is about 100 years ago, our organometallics started with some funky looking carbenes. And by the 1950s, the Simmons-Smith reaction came out using very specifically zinc and this diiodomethane. So I'd like to take a little bit of time with this Simmons-Smith reaction because it is still one of the best ways to make a cyclopropane, and it's still used today to make a cyclopropane. And from now on in synthesis, when you see a cyclopropane, this is how you're going to make it. You're going to use the Simmons-Smith reaction. So let's try and draw that out and see what happens. We kind of learned from our organometallics that our zinc is going to insert into that halogen bond. Let's put it in perspective then. Let's use that. So that part actually happens first. So let's draw that iodomethane, that diiodomethane. It's a pretty funky compound because you've got both iodines here. And then we're going to mix that with zinc. Now remember, the whole point of organometallics is that those metals tend to react quite efficiently and very specifically. In this case, zinc is going to insert and steal those two iodines. So zinc will have an affinity for both of those iodine compounds. And in fact, you're about to make zinc iodide as a byproduct. That's where those are headed. But what's funky is that zinc is only going to take this electron and this electron with those iodines, thus the +2 and the -1. All right, that's where your charges are coming from. So what that translates to is it's going to leave behind, those two carbons right there. Or those two electrons on carbon right there. And we're going to make something crazy funky, and that is called a carbene. Now, if you were in my Gen Chem class and you drew this on a test, I would, of course, slash all kinds of points and not let you draw a lone pair on a carbon. That looks pretty violating, doesn't it? That's what makes this pretty specific. It's called a carbene. They are quite rare. This is one of the ways to make them. There's only a couple ways to make a carbene. Now notice it is neutral, but doesn't it look crazy reactive? It does. And the fact that it's neutral, but it's still missing two things, it's going to do a very specific reaction. It's going to interact with our alkene in a pericyclic mechanism. So once we generate our carbene, it is going to react pericyclic. So let me scroll down just a little bit and let's draw what that's going to look like. Now I'm going to draw it all as one, as the pericyclic, and then I'm going to draw it how you're not supposed to draw it, just so you can track the electrons, but I'll put it in 1980s air quotes. So how do you actually draw your pericyclic reaction? I'm going to line them up like this. and it's going to happen all in a ring. These electrons are going to react with your alkene on either side, and then the electrons in your alkene are going to fill in the empty space created. So literally, that is your mechanism. See how our arrows all go in a ring? That's what pericyclic means. So what do we make from that? Well, let's track those electrons. We just formed a bond here and here with that CH2. That is a cyclopropane. So this is a beautiful way to make cyclopropanes. Now, if we want to talk stereochemistry for this, you've got a nice ring. These bonds have to form cis, especially in a cyclopropane. You can get flexibility in some of our bigger rings, but in a cyclopropane, it just flat out doesn't stretch enough to ever make a trans situation. So your cyclopropane, these bonds will always be cis to each other. They have to be. They can't reach any other way. So let's kind of track our electrons for a second. I'm going to screenshot if you need to. I'm just going to erase right here. How did that pericyclic reaction happen? And could I have drawn this arrow first and this arrow second? Totally. Or could I have done it the opposite and drawn this first and this second? Absolutely. They all end up in the same place. I like to start with the actual carbene, since that's the really reactive pair of electrons. Carbon really, really wants 4 bonds. So if we just take a little snapshot in the middle, remember the point of a pericyclic is that it all happens at the same time in a ring. So let's just track those electrons real quick. If they come in here, you already have enough electrons on that carbon. So they're gonna push these electrons somewhere, right? So let's just draw what would be happening there. In theory, as we form that first bond, what's happening to your carbon? Now you've got 3 bonds and a carbocation. You just used both of those electrons in this bond. So now carbon's missing something. So that's exactly where these electrons go. These electrons now fill in that space. So if they were kind of hanging out right there, now they fill in this space. Of course, this happens so fast that you don't draw that stepwise. You draw that as this whole pericyclic mechanism like this. Okay. Awesome. So when you ever see a cyclopropane in any of our synthesis or anything, the only way we know to make it is this Simmons-Smith reaction. So that's actually awesome. The second you see that in synthesis or homework, there's only one way to make it, and this is your reagents. I love it. All right, let's try a super famous pericyclic reaction next, and that is our Diels-Alder. Oh my gosh, one of my favorites. Look at the year on this thing. We are literally just emerging with ideas of what an atom looks like at that time in history. Think about it. Nobody had even discovered neutrons yet. That was in the 30s. So this reaction has been around for 90 years. This is incredible. Almost 100 years for this reaction. And what's even sassier, look at my reagent. What? Oh, I crossed it out. I meant to highlight it. What? There isn't one. Just a little bit of heat. Now, this is a crazy reaction, but it's phenomenally effective and efficient. We are going to take 2 different starting materials and then look at our product. We're ending up with another ring. We are going to make cyclohexenes. Diels-Alders always make a cyclohexene. They do not make another ring size. So if you see a 5-membered ring, an 8-membered ring, do not use Diels-Alder. They only make 6-membered rings. So But that works in reverse, right? If you're in a synthesis question and you see a 6-membered ring, a cyclohexene, you just put in your mind Diels-Alder. I love it. Now, Diels-Alder is in our textbook. It's on your homework and your study plan. Those chapters can get phenomenally deep into molecular orbitals and molecular orbital theory. We are not going to tackle that. I'm going to keep our Diels-Alder just to predicting our products. You'll notice I'm not going to add stereo to that. If you take an advanced organic class, you'll end up looking at these terms endo and exo for Diels-Alder. We're not going to do that in this class. We're just going to make cyclohexenes and attach everything. We won't look at the stereo component that comes along with it. That gets a little bit too deep for this class. Okay, and there was a huge area in the 1960s and 70s on using computer calculations to do all that anyway, which we're not going to jump into in this course. Okay, so let's try it. Let's see if we can't make a cyclohexene. And let's look at our two partners. So let's do some defining. You'll notice on this side, we've got 2 alkenes. And they are actually in a very specific arrangement. If you were to look at them, it's like they're alternating. This arrangement is conjugated. That is a must. What conjugated means is you have alternating double bonds. If I were to take something like this, that is not conjugated. It is all about your spacing. They have to be basically like this, alternating 1, 3, I could put 5, something like that. We actually in nature, what's awesome is these compounds often with enough conjugated alkenes are substances that are brightly colored to us. So things like lycopenes in tomatoes and keratins and carrots, all of those have conjugated alkenes. So we have to start with a conjugated alkene. You need 2 of them in there. And this is called, and I'm not making this up, a diene. Get it? Diene. I love it. Okay, so we have to have that spacing. We have to have a diene. And then we have just a plain old alkene, just 1 alkene, 1 double bond. This is often called the dienophile, just like our electrophile or nucleophile. That is a dienophile for those 2 partners. And then our reagent is heat. Can you believe that? You take these alkenes, you heat them up, and you make an entire cyclohexene. It looks crazy, but it actually works really well, or it wouldn't have lasted for 100 years. All right, let's draw the mechanism to this, and then let's turn around and practice this one a little bit and maybe put it in some synthesis. So how do we start this? This is another pericyclic reaction. Now you notice I'm going to draw and follow a pattern. I'm going to keep my diene on the left and my alkene on the right. You don't have to, but I find with Diels-Alder it's a little bit easier to follow a pattern. I am going to color code the electrons and the bonds that we're making. And remember, it's going to happen in a ring all at the same time. So you can start with any bond you want. I tend to start with the alkene. Okay, these extra electrons, that pi bond, is going to fill in this space and form a bond to this carbon. All right, there's already electrons there, so they have to move. They are going to flow up here. Okay, but again, there's already electrons right there. They have to go somewhere. They are going to fill in this space left behind on this carbon. Because as soon as we use those electrons, in theory, we'd have a carbocation there. So how do you draw that product? I'm going to color code. All the single bonds are the same. This is a flow of your pi bonds. So your double bond from the alkene has just made this bond. The electrons that were there just made this bond. And then from your alkene, you just made that bond. So notice your bonds are alternating. They follow a flow. They are alternating. and we form a 6-membered ring. Okay, I love it. That is our pericyclic mechanism for our Diels-Alder. They're so fun to try. What's great about a Diels-Alder is we can have flare anywhere. Okay, we can literally have stuff on any of those green spots. So you know where we're headed. How do we make organic hard? We put a bunch of crap on it. So let's try this one. We've got stuff on our alkene, our diene, and our dienophile. So this is our diene, this is our dienophile. I will always follow a pattern. You don't have to, but I find it easier. Sorry, I had to sip my latte. I always spin the diene around. I want to follow that shape or that arrangement in space. Remember, your single bond can rotate because that's how I'm going to draw my mechanism, and that's how I'm going to track the bonds. And then, of course, we have a little bit of flare there. So if you want to number, you could totally number. That will help you keep those straight. And then I put my diene right here. But wait, I have some flare on there too. Do you put it on the top or the bottom? Ah, it doesn't matter. Or does it? Let's draw both. Let's see if it matters. Let's see if we make the same thing or something different. We might have more than one product. Awesome. All right, let's switch to our pink pen. And now let's do our mechanism and let's trace those electrons. I think I'm going to just erase that number right there so it doesn't get in our way. All right, I like to start here. We are going to form a bond to this carbon. We're going to push these electrons right there. These electrons are going to fill in that empty space. So what did we just make? Keep your single bond skeleton the same. We just formed that bond, this double bond, and that pi bond or single bond. Okay, now add your flare. You had some extras on there. We had a methyl right here and a methyl right there. And if you want to include your numbering, you can totally do that. Number all the time if that helps you draw anything that you're drawing. I love it. So that's one of our products. Let's try this bottom one and see if it's the same or different. So I'm going to keep that single bond skeleton the same. Oh, I'm going to add my flare later. Okay. All right, we're about to form the bond here. Push that one up there. Fill in that space there. There you go. Okay, add in our flare. We still had a methyl here. This time, our methyl is down there. Is that the same or is that different? That is different. In fact, we had 2 products for this one. 2 products possible. Now, I am not going to mess with you on stereochemistry on these. Like I said, all the orbital stuff we're not going to get deep into. We just want to use it to make some cyclohexenes in our synthesis. Okay, how do you make organic hard? You draw it funny, you put a bunch of crap on it, and you go backwards. Well, let's do all of that. All right, this one, we put some extras on there. We had an extra methyl here and an extra methyl there, and look at how fun that was. Let's do it again, and let's have it drawn just a little bit funny. All right, let's spot our diene and our dienophile. I am going to take my diene and I'm going to spin it again. I always like to have that pattern. All right, I'm going to number so I can add stuff to the right place. How's that? I don't really care how you number. You just have to be able to add stuff in the right place. So I am going to add right here. I'm going to call... Should I have numbered this number 1 I think that would be easier, wouldn't it? Let's call this number 1, 2, 3, 4. All right, now let's add some flare. We have a methyl here. And on number 4, we have an isopropyl. There's your 5 and your 6. I love it. All right, now let's take our dienophile. And we've got methyls on both sides of that. Okay, now this reaction works better if this is cis, but again, we're just trying to connect stuff. So we will worry about stereochemistry in a later class. And here's our 4. Ooh, that got really hard to read, didn't it? All right, let's switch to our pink pen. Let's draw our mechanism. Notice there are always 3 arrows. They're always in a flow in a ring, and we always follow that same pattern. We just formed a bond here, and we made our alkene there. Now add in your flare. We had methyls here. We had a methyl here. And we had an isopropyl there. Done. I love it. Okay, now could we have made another compound on that? You can try it, but this is symmetrical. So as soon as you flip it, you have the same compound. But you can definitely test it and see and fire me a sassy email after this video if you're able to make another compound. I love it. All right, so how do you make these even worse? Oh, you add some more flare and you add some rings. Oh my gosh, and you draw it funny. Let's do all of it. Isn't this exciting? I love it. All right, first of all, where's your diene? That's where we're starting. Take your diene and draw it like that. I'm going to add some numbers on there so I make sure I've got the right fluff added. All right, let's do 1, 2, 3, 4. So where do we have to add some stuff? 5, 6, 3. I think that's it, right? 5 and 6. Okay, there we go. And then our dienophile has a ring on it. So what? It can still react. All right, follow your process. Let's draw our mechanism. In fact, rings actually react much faster in a Diels-Alder because they're already in the cis conformation, which they have to be. So it's actually, you'll see rings extremely common in a Diels-Alder. Okay, let's start with our process. We just connected here and here, left our double bond there. Now let's add what was on there. Well, this was part of a ring. And then we had a methyl on our number 3 and an ethyl on number 4. Oh my gosh, I love it. How fun was that? Okay, now if you want to, you need to pause now and practice your process, but I want to show you the ultimate in Diels-Alder, and you have a whole homework on Diels-Alder, and that is to take that process and know it so well that you can turn around and go backwards. So if you want to practice the Diels-Alder forward right now, hit pause, do a bunch of these forward. You should have a whole homework, and they're definitely on practice tests and everything. And they will show up in synthesis for sure on your next test because it's one of my favorites in synthesis. So let me show you my process when you're ready to go backwards on a Diels-Alder. Do you notice I had my color coding down pat moving forward? Let your color coding happen to help you going backwards. And why do you give a crap on your color coding? Because now you know what your starting materials need to be, right? These are the bonds that are being made. So that means that this side is your dienophile. This side is your diene. And now we go backwards. So let's do the easy one first. Let's do the dienophile. That is that. Okay, and then let's do the diene. That is that. So these are actually awesome in synthesis questions. Oh my gosh, I'm sorry, this has got to be a sparkle pen moment. You know why? Because you can totally take those and go one step backwards again, and you can make them because you just made them in Unit 2 or in Unit 3, and now we're making them in Unit 4. So how could we make either one of those? Sweet Jesus, can't we make that? Heck yeah, this would be the perfect synthesis question. And then couldn't we make these? Oh yeah. So we're gonna watch for some later videos on how to make these, but just picture, what if you had something like this? Isn't that how you could make that compound? And then let me give you a super secret hint for watching my video. How do you get to that bromine specifically there with a double bond there? One of my favorite reactions. All right, let me pause here.